Welcome to Groundwater Rising. This podcast is all about flooding, with a focus on the forgotten source of flooding, groundwater flooding. Groundwater flooding is the least understood, least monitored and least reported on. It is often left out of the conversation, so we are a podcast dedicated to changing that. I'm Katie Hargrave-Smith from Project Groundwater, and in this podcast I will be speaking to community members from around the UK who have to deal with groundwater flooding and industry experts trying to help them. Together, we will uncover the latest research, innovation and strategies from the water sector, academia and beyond. In today's episode, we're turning our attention to the chalk aquifers of southern England to uncover why groundwater flooding occurs in this region and why it's different to groundwater flooding elsewhere. What is it about the distinctive geology and hydrogeology of the chalk that causes these flood events? This is a highly complex topic, so I'm pleased to be joined by Guy Parker, who brings his 30 years of expertise and experience working in groundwater flood resilience at the Environment Agency. Together, we'll unpack the science behind groundwater flooding in the south of England. Guy, thank you so much for joining me.
Well, it's good to come along.
So to start off, can you tell me a bit about the experience that you have and why you feel like you could talk about the chalk?
My experience in groundwater flooding goes back to about 2000, I suppose. I used to be in a team at the Environment Agency that licensed abstraction. In other words, water companies taking water out of the ground. But there was really bad flooding in 2000. My boss at the time, she sort of picked me up by the collar and dumped me in a flood team, of which I had absolutely no experience. Since then, working not exclusively, but pretty much on groundwater flooding issues.
And so the chalk, can you tell me all about where we find the chalk and why it's important?
Right, okay, so if you can imagine a diagonal line that runs from pretty much Humberside down through Oxford, down to the south coast, just to the west of Dorchester, that sort of area, and then go all the way east and keep going under the Channel, under the North Sea, all the way into Northern Europe. That's the chalk. There are bits that are missing, so obviously you've got the North and South Downs and the gap in between. For the most part, everything to the southeast of that line is chalk.
Why is chalk so important when it comes to groundwater flooding? What is it about chalk?
Chalk is an unusual material. It was laid down in the Cretaceous period. Creta is the Latin word for chalk. And that's going back probably somewhere around about 150 million years ago, so a long time ago. What it is the skeletons of minute little beasts called coccoliths. And as they died, they fell to the seabed and just formed sort of strata. And those strata actually can be up to about 450 metres thick, so it took a long time for that to happen. And the reason it happened very strongly during this Cretaceous period is that the continents were sort of closer together than they are now, with very shallow seas in between them. And those shallow seas got very warm, and it was an ideal breeding ground for these little coccoliths. They're still going on, and they do contribute to carbon capture in the present time. But at this particular point during the Cretaceous period, they really went for it. So what is the chalk? You know what it looks like. It's a white, powdery material with tiny, tiny pore spaces. But it's also heavily fractured. What's unusual, for example, you get sandstones, which got a lot of porous space in them, but they don't tend to be fractured. And then you've got limestones, also porous, but not so much as chalk. And they tend to have a lot of fractures. They're called karstic. And that means that those fractures will transmit water quite quickly. Now, the difference between the sandstone and the limestone is it can take years, even thousands of years in some instances, for the water to percolate down through the grains, if you like, in the sandstone, down to the water table. With the limestone, if you think about people going potholing up in Yorkshire or places like Wookey Hole further south, the response could be down to a weekend. What's unusual about chalk is it has both of those characteristics. It's both porous and permeable through the fractures, and that means that the water can get down to the water table really quite quickly, typically anything from 2 to 6 weeks from the surface down to the water table. And in fact, during really extreme bouts of rainfall, it can happen within hours.
So that's really interesting. Do you mind outlining a bit more about why porosity, fractures, and what the water table is?
Those fractures mean that the water will get down into the store, so that the porous part of the chalk is where the aquifer is. That's where the water's stored, and the process of getting it from the surface down to the water table is the transmissivity of the chalk. It's not homogeneous, it varies, so different members of the chalk family have different levels of porosity and different levels of fracture, but broadly speaking, that's the process. It rains, the water filters down through the fractures, gets to the water table, The thing is the more it rains, obviously the water table will rise. And then as it gets maybe through a dry spell, the water table will just fall away. The water will flow out, and very often there are rivers around that drain the chalk. One of the features of chalk is actually just the lack of watercourses. In most instances, when it rains, the water spreads out across the land and finds its way into rivulets and then into streams and then into rivers. On the chalk, it doesn't do that. What happens is that the water lands on the ground and goes straight down through the fractures into the water table. And that makes chalk a fabulous aquifer in terms of our public water supply. We'd be in real trouble as a country without that huge reservoir underground of stored water.
Yeah, it's a very interesting one that we both worried about having not enough water in the aquifers, but equally worried about when there's too much water in the aquifers.
In the same year as well. I mean, it can fill up. It just changed. At the moment, it's very dry. We've had a very, very dry spring and summer. Last year, we had a very wet winter, significant flooding. And it can change quite quickly through that process. One of the things is it's a fairly unique feature in southern England. Although chalk, as I said before, it underlaid the seabeds over much of this massive continent, Gondwana land, or Pangaea, it's not the case that happened everywhere. That has to do with continental drift, if you like, that Africa has been slowly crashing into Europe over the last few million years. What that's meant is obviously it's formed the Alps and the Pyrenees. But by the time you get that bit further north towards us, it's become rolling hillsides. So you get in southern England, you get these glorious rolling chalk downlands. Whereas if you go further away and more sheltered perhaps by the Alps and the Pyrenees on continental Europe, it's really flat. You get Pas de Calais, for example, which is this very flat chalk landscape. But those hills, that hilly landscape has been compounded. We talked about that line that goes from Hull down to southern England. Not dissimilar to that is the one that went from the Wash through to the Bristol Channel. And that marked the edge of the ice flow. So everything pretty much to the south of that line was tundra. It wasn't really ice sheet. You have to go further north to have the ice sheet. And what happens in that sort of circumstance is during the summer months, the ground would thaw to a certain extent. And that meant that rivers would form. But it couldn't percolate down into the chalk as it normally would because the ground underneath was frozen. And that meant that because we got the hills created by this sort of continental drift, the rivers that formed created river valleys, which were lined with gravels. That means we've got hills in the chalk. We've got river valleys with no rivers in, because now it doesn't occur like that. Obviously, we don't get that freeze-thaw process. That's what actually makes southern England almost uniquely prone to this extreme groundwater flooding. It's the combination of the hills, so that the water table will rise up above the valley bottoms. The valley bottoms themselves are pretty much where we live. We live down there because in a colder, drier period, that's where the water that we need on a day-to-day basis was most accessible. I think that probably in warmer climes, so in maybe the Roman period, people were able to live higher up. People lived in hill forts and so on, whereas more recently, over the last few hundred years, when it got colder, people moved down to the valley bottoms because water was more accessible. The thing is that when the water table rises in hillsides, it creates what's called head or hydrostatic pressure. The volume of water drives water back up through the valley floor. You can imagine there's a sort of balancing act. Water is always trying to form a level. That pressure downward on the hillsides can create quite active springs along the valley floor.
So the way that the water table works, because I think when we try and picture it in our heads, like we'll very simply picture just a straight line underground, but that's not how it works, is it?
It follows the contours of the land, broadly speaking. So if you can find that there's maybe a 50-metre difference or more between something up a hillside and then down in the valley bottoms.
This pressure you're talking about, so does that cause the water to rise more at the valley bottoms? Does it rise in the hills? Where is that pressure pushing from?
So what happens is, you can imagine on a seasonal basis, when it rains, the water table tends to rise, and the recharge, that's the period of the year when the water table rises in response to rainfall, happens in the winter. It can happen in summer, but only very rarely. It has to be extreme rainfall for it to get it to rise in the summer. In the summer, evapotranspiration, the plants soak up all the water and chuck it back up into the atmosphere. You don't get that recharge during the summer months. In winter, The water table responds usually from about October, the start of the water year, if you like. Sometimes a bit later than that, maybe as late as December. But there's nearly always considered response to a rise in the water table. And as the seasons change, so you'll find that the river, the winterbourne, if you like, follows the water table up and down the hill. One of my first jobs in the Environment Agency was doing winterbourne surveys. Get out of your car and you walk up a hillside following the stream until you get to the point where it goes dry. And you mark that on a map, and then you go back down and you do it again further around. And by joining the dots up, you can actually develop a contour of where the water table roughly is. But it's quite a good indicator of how high the water table is compared to other years. That was quite a useful learning curve, really, because we got to know where you might want to put boreholes to understand how high the water table is around the place.
So you were sort of mapping where the winterbourne was starting that year?
Yeah, that year, and then you can compare it with subsequent years, because that was quite easy to do and quite cheap. I used to do it on a horse, actually, because it was easier to get around. It was a broad understanding of where the water table is. What we could then do is when we had a bit more money, we were able to drill boreholes which were sort of right up on the top of what's called the interfluve. That's right up on the sort of hill between sort of rivers and streams. And then you get the full range. You can see how low it gets in summer, right the way up to the high winter levels. Climate change has made a big difference. It's something that's quite visible. The earliest records that we have really go back to about the 1840s. Usually in vicarages, some vicar would go out every Sunday morning after service and dip at the well at the bottom of his garden. And we've got quite a good record in those instances. And there are about 6 or 7 of these places dotted around the country. We can use that to show how the water table has increased. It's also decreased so that there's a bigger range than there used to be. We'd see more dry spells and more wet spells, broadly speaking. So if you average it out, it hasn't changed an awful lot. But as I say, the swing between the low point and the high point has significantly changed. Since about 1990, really, that was when it really started to be noticeable. Mostly on the chalk, there were only 2 instances of groundwater flooding before 1990. So one in 1915, that was the last time Salisbury Cathedral flooded, and Winchester Cathedral flooded the same year. And then once in, I think, 1946. But apart from that, very few records of groundwater flooding. In the 1,000 years that Salisbury Cathedral had stood, it had only flooded about 12 times in those. So about once every 100 years. It hasn't flooded since 1915, but the surrounding area has flooded, I think, 8 times. That's an increase in frequency of note.
It is tricky with groundwater because a massive event, it'll probably be recorded as groundwater, but is there a chance that there has been groundwater floods but they've just been on a smaller scale?
Yeah, it goes both ways. It's very difficult to tell what caused a flood historically. We know that a great deal of water, a very wet winter, will cause a rise in the water table. That's a straightforward relationship. It's difficult to know some of the other impacts. So we know that the amount of water we abstract does make a difference. We take a lot of water out of the ground for public water supply. That's a fairly recent event, certainly since the late 1800s. And in fact, we've stopped doing that because we're not as industrial as we used to be. So we're not using vast quantities for industrial processes, which means that there's a sort of rebound in the water table, which has caused problems in London, but also in mining areas as well, further north.
And you mentioned earlier that the chalk is very kind of special in the fact that it does both extremes, so it both moves very slowly and moves very quickly. Can you talk a bit more about that? How does that work and how does that impact flooding?
It's all about the actual intensity. So if you get a very wet winter where it just rains a bit every day, that will gradually top up the aquifer. And it can take weeks to get there. And that process isn't uniform. Where you are matters. So the further west you are, the more it rains. So the chalk in the west of Dorset, bits of Wiltshire, up through Buckinghamshire, so on, that sort of western fringe of the chalk, it rains more than it does in East Anglia. A lot of the chalk in East Anglia, it actually isn't on the surface. It sort of underlays the rock. It is a feature, if you like, of the southwest of England and the west of England that it gets more rain, so it recharges more quickly. That's one factor. The other sort of real issue, I suppose, is the chalk itself. It's not homogeneous. Some of it's more fractured than the others. So the fracturing acts as a conduit to get the water out when it's flooding, but it also means that it charges more quickly when it does rain. So it's sort of quick in, quick out if it's heavily fractured. Because it rains more, that means that the fractures tend to be bigger the further west you go. There's a sort of a compounding issue there. And then the other thing is those hills that we've talked about, you get rainfall that's associated with orographic rainfall, but that's where air that comes in off the sea rises up. It tends to rain more heavily on those exposed hillsides. It doesn't really happen much in the summer. It can do. In July 2012, near Weymouth, down on the south coast, there was 160 millimetres of rainfall fell in 24 hours. The water table rose by 16 metres in response to that over 2 days. So it can happen in the middle of the summer very fast. It's unusual, but it can happen. So to say it can change literally almost overnight if you get a really intense bout of rainfall. And the same thing happened in July 1955. On the 7th of July, 260 millimetres of rainfall fell in that same sort of area. And that actually, Martinstown, it's the UK rain day rainfall record. 11 inches fell in 24 hours. And interesting, there are two rivers sort of almost side by side. One is on the chalk, the other one isn't. The one that's not on the chalk flooded quite badly within hours, almost instantly, because that sort of volume of rainfall. But the South Winterbourne, which is just over the other side of the hill, didn't start to flood until a day and a half, nearly 2 days later. So you can see there's a difference in response to really intense rainfall between a runoff-driven catchment and a chalk catchment.
So is that in the non-chalk area, the water is running kind of directly into that river, whereas in the chalk it's going into the chalk?
Yeah, absolutely. The other river, not the South Winterbourne, the other river is actually the River Wey, which runs through Weymouth. Chalk at the very top end then rapidly becomes a steep-sided clay-based catchment, and you get a lot of very rapid runoff from that. Two rivers almost side by side, responding very, very differently to intense rainfall.
And when you think of the chalk underground, groundwater flooding, it reacts after like long periods of heavy rain. That's when we tend to see.
Yeah, there is a memory. So if you get one wet winter and then a moderate sort of average British summer, the water table starts off a little bit higher at the beginning of the following recharge season. So you can have a memory from one season to another. The rate that the chalk loses water through the summer period is fairly consistent. Because you don't have any recharge, the water can get out through the fractures at a fairly consistent rate. If it starts the season very high, it'll just take longer for it to drain out through the system, but only because it's starting from a higher point. The actual flow rate remains pretty much the same.
And we've had 2 very wet winters, so it's sort of like you're hoping for a dry summer maybe so that it can fall, but you also don't want a dry summer because drought.
The dry summer will make a difference, there's no doubt about that, partly because we tend to use more water when it's a dry summer, whether it's through farmers having to do some spray irrigation. We just use quite a lot of water when it's very hot. It's not critical, generally speaking. One dry summer doesn't really cause a drought on the chalk aquifer. It would take 2 consecutive dry summers and a dry winter in between to cause a problem. It's the dry winter in between, really, that does it, not the dry summers. If the amount of recharge as a total of the annual volume is less than 10%, having a really dry summer compared to the 90% that is taken up during the winter, it doesn't really signify.
So it'd be, if we have a dry summer this summer and then a really wet winter, would that still...
We would be back where we started. It's a bit of a memory, but it's not that good.
There's a kind of seasonality to groundwater flooding, you said, like it happens more rarely, but have you seen a pattern in frequency recently?
There's no doubt about it that since about 1990, I suppose, there has been an increase in the frequency of groundwater flood events. You can possibly say that this is just a sort of a normal oscillation, but I think probably there's more to it than that. The rainfall we've had over the last 30 or so years is in excess of what people experienced before that, and that's seen in fluvial flooding as well. You know, the number of fluvial flood events has increased over the same period. Warm air, it has been warmer, holds more moisture than cold air, and particularly in winter, if you have warmer winters. I mean, we don't get in southern England, we don't get snow very often. I can remember as a child, most winters there was a good bit of snowballing to do. It just doesn't really happen so much now. There has been a change generally in the climate, and the water table responds accordingly.
I do think even when I grew up in Kent, I remember more snow when I was younger than I do recently. Like, I can't remember the last time I saw like enough snow to have fun in the snow.
okay, so that's in our lifetimes. But if you think that it wasn't that long ago that people were skating on the Thames, well, I mean, that just is very, very unlikely at the moment. And if you think longer term than that, so going back 2,000 years during the Roman warm period, the Romans were growing grapes in Yorkshire. We're starting to be able to do the same thing now, but you wouldn't have done that in the early 1800s or even in the sort of 1300s. So there have been warmer and colder periods. That is climate change, whether it's man-made climate change or natural climate change. It really doesn't signify anything. But the water table will respond to warmer winters. I mean, there have been quite a few climate change projections, and unfortunately the jury is still out, really, as to what the impact will be. There are things that we do know. We know that what will happen is that we will experience warmer, probably drier summers, but with bouts of more intense rainfall. Well, from a groundwater point of view, that probably means more recharge in the summer than you would otherwise see. Normally speaking, you don't get recharge in the summer except during intense rainfall. So at the very least, I think it'll make no difference. The other thing is that we're going to see warmer winters, which will mean wetter winters, inevitably. And I think probably shorter winters. So we will see vegetation starting to grow earlier in the year and still be around a bit later in the year. The harvest tends to get a bit earlier so that the ground becomes more exposed. A lot of the chalk downlands are quite arable. That means that potentially they could actually start to see recharge at an earlier point. But I think probably we'll have shorter winters, but wetter. So more water, maybe as much as 10% more water over 4 months instead of 6 months. And there's a problem there. If you can imagine a graph, along the bottom you've got a time series, so in weeks or something like that. And then on the vertical axis you've got the depth of water. Any flood hydrograph, there's a relationship between time and the depth of water. It's called a depth duration curve. The thing is you can't really influence the amount of water. He upstairs does that. That's his decision as to how much rainfall we're going to get. But time, on the other hand, is something that we can control to a certain extent. People talk about natural flood risk management, and that's about slowing the flow. In other words, extending the time it takes for the water to get into the river, if you like. So you can plant trees and do various things to slow the having. In a normal catchment, not so much on a chalk catchment, but in a normal catchment. So there's this relationship that if you can extend time, what you do is reduce the flood risk. And it makes sense. If you've got a bucket of water and you empty it on the floor, you get a flood. If you have a pinprick hole in the bottom of it, you get a damp patch, which probably won't do much damage. So that's the difference, if you like, between a quick flood and a slow one. Now, the problem that I was talking about is that if we're going to reduce the number of winter months but increase the rainfall over them, effectively what you're doing is not extending the time period, you're compressing it. And that curve, that nice sort of parabola that goes up as it starts to flood and comes down again, instead of being flattened out, will get pushed up. And I think that's probably what's been happening, why we've seen more groundwater events over the last 30 or so years.
Because I think with groundwater flooding, we always say that you need long periods of heavy rain, but what you're saying is actually it's not the long periods really that matters. It's normally you need a long period to reach that quantity of water, but that quantity of water is being reached in shorter periods. Which
is why we're seeing more flooding, even though winter rainfall may not change that much. It doesn't have to. It just needs to reduce the amount of time that it takes for that rainfall. You can see groundwater flooding in 48 hours if you get a stupid amount of rainfall. But that same volume, if it's spread over 6 weeks, will barely make an impression. It's actually the intensity, not of a rainfall event so much. So with typical fluvial flooding, 3-4 really horrible wet days can cause really bad flooding. With groundwater, it's 3 or 4 really wet weeks. So it's not that same intensity. It's building it up over a period of time. If you can imagine a bathtub, okay, so this is probably the best analogy. You've got a bathtub, fill it up with golf balls. That's the chalk with all the little pores in between, so that you're storing the water between the pores in where all the golf balls are. And you've got two things. You've got a drain at the bottom. So you've taken the plug out and you've turned the taps on. And in the summer, the taps don't actually produce too much. And the water that's there drains out through the plug hole at the bottom into our big chalk rivers. So that's where it sort of drains out through. And then in the winter, you turn the taps on a little bit more and the water level starts to rise up through the golf balls until eventually it gets to that overflow. And then you start to see the springs all starting to go, and winterbournes are flowing, they're flowing into the rivers, and you're starting to see the rivers really getting quite full. And then as it keeps getting those higher levels, maybe to the end of the Ice Age, when the water table was very much higher, at that point you could perhaps see the spring lines which we don't see anymore. But when it gets up to that level, everything starts to flow again. And that's when you get a wet bathroom floor. In other words, the water table has risen above the level of the top of the overflow, and it flows out over the top. And that's when you get really bad groundwater flooding. The sort of thing that we need to think about, though, is the storage of the chalk. It can be up to 400 metres thick, and it runs all the way up to Humberside. Each cubic metre of rock can hold between 300 and 400 litres of water. It really is important to us in terms of our public water, so we need to look after it. Equally, in drinking it and using it, we are preventing some of the worst of the flooding. Hand on heart, I think probably the solution to groundwater flooding is trying to find a way of taking the water when there's too much and preserving it so that we can use it when there isn't enough. Now, that may mean that we have to think about how we can move it, because storing it in the ground isn't obviously an option. And there's no point in storing it on the surface because it'll just go straight back through into the ground. So I think the answer is possibly trying to find ways that we can move the water to parts of the country where there is a shortage. So in 2019, in the Wessex area, there was really significant groundwater flooding, and there was all the way up through the chalk into Bucks and Berkshire and so on. Devon and Cornwall, on the other hand, were still in a drought situation with no water in their reservoirs.
But the issue that is there, the sheer quantity of water during those floods, is how would you move that? There's a lot of questions that poses.
Well, exactly. I'll give you an example. There's a village on the edge of Salisbury Plain, which is very close to a water company abstraction point where they supply most of the water for Yeovil, a considerable town. And that water is licensed, so the abstraction is licensed. The licence expires each year at March, so they're allowed to take so much water every year until the end of March. They shouldn't go over that, and they can be fined if they go over that abstraction amount. March 2019 was very, very wet. The water company had reached its limit, and they stopped abstracting. And instantly, properties flooded. It didn't take an awful lot of water, just pumping the water out, to keep the water table below a critical point. Obviously, the answer was to change the licence so that actually now if the water is over a flood alert or a flood warning threshold, then they can fill their boots so that we don't end up with a rather ridiculous situation where we cause flooding because people stop abstracting. We need to think more about how we can use that balance between abstraction and flooding. Bearing in mind that it tends to be communities, fairly isolated communities, that are worst affected. So you can target where you might want to take water from to reduce the impact of flooding. Big problem though.
Yeah, and abstraction and flooding is a tricky conversation because there's a lot around it, and it's one that we're hoping to actually have an episode on. There's been discussions around that.
Not least if you start putting very alkaline water and pumping it up to Lancashire where everything's very acidic, you're going to cause all sorts of issues in terms of the biodiversity of the local area. So it isn't an easy solution. But I think some means of trying to balance the water is really the only long-term solution if it starts to get much worse than it has been over the last few years.
Well, thank you so much for joining me today, Guy. And thank you for listening to Groundwater Rising. Please hit the subscribe button on your podcast provider, leave us a review, and tell your friends and colleagues about us. Do you have a topic you'd like us to focus on Groundwater Rising? Or would you like to join me to share your personal groundwater flood story? Please email me on groundwaterrising@projectgroundwater.co.uk. That's all for now. We will be back on the last Thursday of next month with another episode of Groundwater Rising.